Okay, we're going to start. Is the microphone on? Yes. So today we've got Daniela, who's come all the way down from Glasgow, originally from Chile, even further. She's going to be talking about extreme values, soil. So can I hand over to you? Thank you.
Right. Thank you. Can I try to hide this?
Yeah.
Video plugin. Yeah, much better. Right, so thank you very much for the invitation. I hope those online can hear me well. So I'm going to talk about something that kind of slightly different application to the one that we usually have when we work with extremes. And this came from a collaboration with the BGS, which is the British Geological Survey. So before we start, acknowledge my collaborators. So this project is part of Daniela PhD thesis. She's a student of mine at the University of Glasgow. She's been co-supervised by Professor Marian Scott. As you can tell, in order to be a PhD of mine, you need to have my own same name. I kind of have PhD that don't have my name. She's actually my first PhD student, is about to graduate this month. And we got the support from Ben Martin from the BGS that helped us kind of making sense out of all the results that we were having. Right, so what I would like to talk about today is a case study to show how we can adapt extreme value theory to geostatistical problems without temporal replicates, and combine it with classical statistics to model not only the extremes, but also the bulk of the distribution. And this is particularly different, as I was saying, to the usual applications of extremes, because the genesis of extremes assumes that you have replications. So assume that whatever you're observing, being like univariate, multivariate, or spatial, has replications over time. And in this particular application, that's something we usually don't have. So the motivation comes from understanding both the extreme and non-extremal behavior of unreplicated spatial processes. And the reason why it's that important is usually because extremes are related to risk. Now, classical modeling tools to try to model unreplicated spatial processes are based in the classical geostatistical models around the Gaussian processes. And as you can imagine, the Gaussian distribution being very light in details means that it's not able to capture extreme observations very well. And it usually assigns probability 0, close to 0 to very extreme events. On the other hand, extreme value models are more appropriate as I was saying, they rely on replicated observations at each location. And of course, the focus is only on extreme, however you define them, but it's only on extremes. So the aim of this project is to model unreplicated bivariate spatial data to capture extreme and non-extreme observations. Right. So towards the end there, I introduced a new keyword, which is bivariate, and that has to do with the data that we had at hand. So we are looking at the very heavy metal contamination of chromium and lead in the Glasgow conurbation using the G-based dataset provided by the BGS. And here is a kind of a summary of the data. So on the right-hand side, we have maps of chromium, and then on the left-hand side, we have a density estimation of the log transform from your leg. And what we can see, well, first of all, one of the features that, again, we have single realization time. We have skewness and a long tail distribution. If we look at the map, we have some patterns. There are some clusters here of machine values around the center, for example. So there is some spatial correlation, spatial behavior that we want to capture, of course. And then on top of that, we want to be able to also capture the dependence between these two contaminants. Right. So hopefully now you are sufficiently motivated for what's coming. And this is slide just to tell you basically what's next. So first I'm gonna do a small summary of what I call the journey that we had trying different tools to modeling this data set. Then I'm gonna introduce our proposal, this spatial mixture model for unreplicated extremes and non-extremes. And then I'm gonna conclude. Whenever I'm in talks, I don't know about you, I always look at the number in the bottom right corner. Like that gives me hope. Because yeah, we know that. So to help you on that, I now what I tend to do is to tell you basically how much time I'm going to spend in each section. So hopefully you have something to aim for. So the main focus, of course, of this is going to be on the second part. And after I show you the model, I'm going to detail kind of step by step the different results that we had. Right, so let's talk about everything we did before we came to our final model. And note, it's not really everything, but it's, I think, the most important parts, I guess, to show. So first thing we consider are non-extreme value models, because we need to start from kind of the classical approach and not only classical, but what people are using until today. So we look at geostatistical models. So like I would say, these are the most common models in soil science, and they are based around the Gaussian process. And they are, of course, targeting the mean. And kind of a flexible way to deal with those is when you put a smooth term, for example, in the mean. So we did some exploration. The ones I'm showing you here on the top, we have non-stationary gradient. At the bottom, we have something similar about where the mean includes some smooth terms. And on the left here, we have the results of the gradient, and then we have some QQ plots here in the middle, and then the same result for lead. We have chromium on the left, and then on the right we have lead. And the results are as far as expected, so we were kind of guessing that we will have a very bad behavior there. Interesting, we are able to capture some of the spatial dependence that we saw in the maps of the data, but we know that it's not very good. It's not very good, right? So the next thing we did is to look at extremes. And for the kind of application we have, it makes sense to define extremes as exceedances over a high threshold, because we are looking at soil contaminant. So the environmental agency has threshold values that have been defined, and we're looking at exceedances over those threshold values. And there is very nice theory around threshold exceedances, and that was said that under my assumptions, the limiting distribution of threshold exceedances is given by the generalized Pareto distribution, which is the one that we have here on the right of the equation, and is characterized by scale parameter sigma and shape parameter psi. So, because we were only looking at extremes, we wanted to have an idea of the level of extremal dependence between chromium and lead. So what we did is to kind of forget about the gold values. We only look at extremes, and particularly we look at the interaction between extremes of chromium and lead. So one way to characterize extremal dependence is by looking at this dependence measure chi that we have here, which is a conditional probability of one component being large given that the other component is large, right? So what we have here kind of inside the probability is just a transformation into the uniform scale. So these FY1, Y2 are the marginal sphere. So we can look at this as a measure of extremes in the uniform scale. Therefore, extremes are associated to values close to 1. So what we did is to model the dependence between these contaminants, and we use a bivariate version of the field. If we compare that bivariate version that we know is the limiting distribution with a model that is slightly more flexible, it's not the limiting model, it is on the way to the limiting model. Sometimes these types of models are called sub-asymptotic models. It's called the exponential factor popular model that Rafael Husserl, who was my peer during my postdoc, and I proposed. Now, the difference between these two models is that the exponential factor popular model, which is the one that you see in the green here, is way more flexible when you look at the extremal dependence. So the bivariate TPD, which is the one that you have in red, orange, it's just a straight line. So it's always the same, independent of the level of extremeness of the event, which is the one that we have in the axis. And then what you see in blue or purple here is the empirical version of this conditional copy. Yes.
I'm just trying to understand this graph. If Y1, Y2 were independent, then what would I expect here? I would expect that pi to be uniform around 0.5.
So if they were independent, basically what you would be saying is that Y2 being large doesn't affect Y1 being large, right?
Yeah, so that would manifest as probability would be uniform 0.1.
As the guide means 0.
Sorry.
So that would be chi equals 0.
You can have 1 minus e.
Yeah.
What in the uniform scale? I'm sorry. Yeah, it would be it would be 1 minus.
Yeah.
Right.
Yeah. So for each u it would be.
Yes. Correct. Yeah. Correct.
But that's because I guess the x-axis is not from 0 to 1. Here it is the. Anyway, straight line, not going with it.
Yeah.
And if they are strongly correlated, if they are the same, then this would be. Would be 1, everyone. Yeah, you guys. Thank you.
When you calculate this one-time empirical model,
Sorry.
when you calculate this the
Yeah.
one-time calculation, is there some ways of chemical correlation of them? Because if you estimate the empirical seed temper, then you also use the same data to calculate the probability, you're going to either overestimate or underestimate this as well. But if you use the data to calculate the CVM, we're using the data to calculate quantifiers. Then you're also using those to get the probability of that's strange.
I'm not aware of any indicator that you might observe.
I mean, it's literally the first time I see this plot, so I'm sure.
Right.
Just it's just okay. Look.
Like it's fairly standard to do it that way, to be honest.
So this is the standard.
Yeah, kind standard when you do empirical version of it. Yeah.
And it describes the difference. They're actually in some way answered. One is big, the other is.
Right, it's like the kind of a level of extremeness of it, like the level of dependence is decaying. Yeah. Yes.
There's sites that I have, like, I'm trying to take supplements. Like, I'm taking iron, I don't want to take calcium at the same time, right? You got lead and something from it, right? So
Yes.
does lead help where we get lost? Is there some sites that I'm worried about? Or is there some reason why they're coming together?
So I'm sorry, I don't think I understand the question.
Does lead keep the chromium out? Or if I know about lead because it's gas issue, put in the soil, right? I know a couple for sure. Okay, so if there's some science, there's a scientific reason why.
Right, that's why we're looking at that. Yeah, so that has to do with kind of a historical kind of contamination. So I remember at some point we got the info from Ben from the VHS, and he was expected to see something like that because of the characteristics of Glasgow being a very industrial city back in the days. But that's as far as we got regarding like the reason why that's yeah. Second?
Did you get somebody you did just
Yeah, there is something slightly like unusual happening here, definitely. And that has to do with the lack of data. So we need to be kind of careful in the way we prepare this part. Yeah, definitely.
Okay, 5%. What's the score?
Oh, we have so many different names. Coefficient of tail dependence is one. You must cover the next. Yeah. Different people will call it differently. This was actually proposed by Harry Joe in 1997. Yeah, part of a popular paper for sure. Right. Okay, so then let's finalize here.
I'm sorry, can I ask one more question? This is battling with this flow. And say I'm looking at stroke is 5, and that 5 thing is 0.4. So this thing, the probability that Y1 is exceeding its 80th percentile is actually lower than it would have been if we didn't know why it's right? So all these values are below the X and Y. Is that right, what I'm saying? Yeah, but this is a lot lower, so it,
Should be.
or 1 minus Q. I see, sorry, that's what I was missing. 1 minus. Yeah, it's greater than. It's not less than. Okay.
That's great.
Yeah, okay. Yeah. Now it's. Okay. So as long as that value is above 1 minus, then there is some kind of.
Yeah, exactly.
Yeah. Then my mind I have it this way, and that makes sense. Okay, thank you.
No problem. Right, so now the problem with this approach, first of all, we're only looking at extremes where discarding a big percentage of data. The other problem is that we are completely discarding the spatial component, right? So, as I told you before, we want to model this in space and also the dependence between the two components. So, discarding the spatial dependence, basically what we're doing is like pulling all the data together. So that's not really ideal. So we need to find a way to kind of do both things.
The soil, it's a soil height issue, because you're gonna have the contaminants, right? And over time, they're gonna seep deeper into the soil, right? Where you taking the height of the samples?
So these are samples that were taken many years ago. It's and there is a standard procedure to do it. I can't really tell you what's the depth of that, but it's the same everywhere. Yeah. Well, I should mention that the reason why they only do the measurement once is because concentrations of this type of contaminants don't really change much with time. So it doesn't make sense to do this across time. Okay, so moving on to our proposal. So after many discussions, we kind of, how can I say this? So what we are proposing is a mixture distribution. But what I want to say here is that the mixture distribution makes sense if you look at how heavy metal contaminations are usually explained. So the way they are usually explained is that there are a mixture of background concentrations and elevated and extreme concentrations. So this is coming not from the stat, this is coming more from soil sciences that say that we have that kind of mixture. So the idea of mixture distributions, as we understand them in stats, it makes sense. So what we do is we model the body and the tail of each contaminant as this mixture model. So this is, for example, just for chromium, we will have a mixture between a body density, which in our case would be Gaussian, and this Y is in the log scale, so I'm looking at the log of chromium and the log of lead. So the body will be Gaussian, because we know that if you only look at the body of the distribution, the Gaussian assumption actually makes sense. And then we're going to combine it with a density for the cell, and that will be the GPT distribution, so the Pareto distribution. So that will model each contaminant, quote unquote, independently, but we want to link them in some way, and the way we're going to link them is through a latent field. So we will use a latent framework to link them together using shared component. So in that way, we are not modeling directly the dependence, but only through this shared component. Right. So this is a summary of the methodology, the kind of a modeling framework, and this is the same up to a certain point, up to here basically. It is the same for the first and the second component. So I'm only focusing on the first component, and then I'm going to make the link to the second. So we start from the top. We have FY1, so Y1 can be log chromium, for example. It's going to be a mixture with weight P1 of the body density, which we know is going to be Gaussian, and the cell density is GBD. Now, the Gaussian density is going to be described by a mean vector, which I'm calling eta and a dispersion or a variance parameter. And in this ITA vectors where I kind of use a linear predictor structure, where I'm gonna have covariates on one hand, which are these xj that we have here with fixed effects bcas, of course an intercept, but most importantly, I'm gonna have this spatial effect. So hopefully this set will be able to capture spatial structure of the bulk of my first component.
That led to,
Yeah, so this can be, for example, chromium, log of chromium, and a log of thing.
and what are the covariates?
So covariates, we have like distance to main roads. I think that's going to be like the main one. Yeah. Right, and then for the TPD, there we have a situation, right? Because again, we face the problem of we need to have temporal replicates, but we don't have them. So we do something to circumvent the need for this replication. And yeah, it's kind of like the price we have to pay it. So what we do is we assume the spatial stationarity of threshold exceedances. We pull them together and we feed a TPD. And that TPD, of course, is going to be a stationary one. Then we use that TPD to transform these scale values to a common Gaussian scale using the probability inflow. And this is what I have here as FT1 star. So this will be basically my exceedances. I'm gonna feed them with this GPD with stationary, and then I'm gonna transform them to a Gaussian scale. Now, in the Gaussian scale, I'm gonna put some structure into the mean in a similar way to the one that I did for the bulk of concentration. So again, I'm gonna have this linear predictor structure. And then here, I'm also having a spatial component that will try to overcome this simplified way of dealing with it. Because here, what I'm doing, forget about the spatial extent, and here I'm trying to address it again.
So transform to the Gaussian scale.
Yeah.
See, what F star T1 space is that?
Again,
What is F star T1?
so F star C1, that is a normal.
Why is T1? Find it interesting. Why is it?
Yeah, so this is the GPD.
Yes.
This is the GPD.
Why is it observed?
Where
Once I look into
right.
and after you did together anyway, once you get it's based by the gas so yes.
Yeah, this is yes. This I mean the probability to conform is applying the CDF to your observation, right? And then you have to apply the inverse of that of the whatever you want to. So it should be the other way around, right? It will be capital 5 minus 1 and then F to be Gaussian. Exactly. Yeah.
But these are models separate, right? There's no Gaussian there.
until then, like, well, this is nice actually, because this is a set where I'm trying to link them together. That's what I'm going now. So, right. So basically, up to let's say here, we are pretty much modeling this independently. But what we do to link them is to say the tails will be linked. So the tails, if you look at the linear predictor structure for the two tails, they are sharing this spatial component here. And the lambda that we have here can be seen as a measure of the strength of that spatial relationship between the two tails. Now, you might be wondering, why are you not doing the same thing for the bulk? And that's a fair question. We tried many different things, many different sharing components. We realized that what makes sense that both share with both and tail with tail. And on top of that, we realized actually adding a shared component of the box doesn't really add much to the model performance. And it increases the complexity quite a bit. So we decided to just go for a link of the thing. Now, having said that, although we don't have shared spatial effects between the balls, there is still some sharing of spatial information through the covariates. The covariate in this case is spatial. So there is still some sharing of information, but only through the covariate.
Can I ask that? That joins, that dependence is one way, right? First, it's y1, and then extract that. I mean, the modeling, or do you do this simultaneously?
No, it's done together. It's done together because you kind of want to borrow strength between two in order to estimate the spatial effect and the
The dependence is a bit different, right? Or is it actually in the end the same? See what I mean? Like, it's not that you have one common component and then you have an extra set 2 and an extra set 1. Because you could have had a set 0 that's kind of the common spatial structure and then one has a component.
Well, we have something like that here actually. You can see the second component has an additional spatial effect.
So is there asymmetry? What I'm trying to say, if you swap them around, get the same results.
No, that's a good question. That's something that we actually learned. There is no symmetry. And there is always one that is going to perform slightly better than. Yes.
So it's just saying that both can learn the same way and it's both next to the same gas station, but one has a bunch of lead, then you send a double type of lead to the out to the street, that was like. But you have two different things here, right? You say the covariates are shared, it's the same covariate, right? Covariate is how close they're to go, right? Which means same gas station. It's given from right? And then when it's extreme, it's something else, right? There's some dogs stuff. Or some other reason.
Yeah,
Is that
that's a reason. Yeah.
what this is saying? Is something else, you're saying you're prescribing that something else is responsible for the extremes of, is that in the model?
That's what I'm trying to do when I have different distribution for each part. Yeah. And the spatial effects are trying to do the same thing. That's why there are different spatial effects. The one that you have on the balls are different from the one that you have for the tails. So we are some way trying to capture that. Yeah.
So what does come out of curiosity? What Terry was saying, which covariates do come out? Significant for it. What are the differences between the base and the screen? Which covariates come out? Are they different? I'm just curious about the applications, not a technical question. So is the distance to the road, for example, equally important for both all the pieces?
Right. Oh, that's a good question, and the answer is for sure in the paper. Remember exactly? I'm sorry, I don't remember. I do remember there are differences, but I can't really tell you which one. And
Were there other covariates that were considered? I mean, what else
uh,
drives types?
so
Yes.
yeah, I mean, I have, I have the idea there was another one because there was whole process. Or like the one that comes to my mind because it was the one before when I was the road. And now that's something that we had to construct, so that didn't come with the data set.
Yeah, yeah.
So it was not an easy task, to be honest, to kind of construct those pictures.
And what's the spatial range of the grid?
So
That city, sorry, I didn't understand.
yeah, I can show you the map again. So it's the Glasgow conurbation area, which is kind of a greater Glasgow. So Glasgow is here in the center, but this it's totally greater Glasgow, which is a bunch of other smaller commuting towns to Glasgow.
Yes, maybe all this stuff.
Yes, we tested, and yes, thank you for that. Yes, we did that. We also tested the distance to the river, but it doesn't turn out to be important. Yeah, thank you for that. Right, so right, so I have only one line regarding inference, and that's because well, like I said, I didn't want to focus much on that, but inference for this model was possible using a combination of what's called the conditionally Gaussian field framework that was proposed by the Virgilio Gonzalez Howard group. That was proposed as a way to fit, well, one of the applications was to fit mixture models within the ILA framework. So if you don't know, I don't know how much you know about ILA, but yeah, fairly familiar with ILA, so I don't have to tell you much about that. But then if you know ILA, you recognize the kind of a latent framework structure that we have here, right? Okay, so that means that the model is fitted conditional on mixing weight. That at the time we fitted this model, that was the only way to do it. Now there's an improvement in ILA that allows you to fit mixture models under certain conditions. Right. So following up on that last comment, the first thing we need to do is to kind of classify the observations into body or tail. So, as I mentioned, the model fitted conditioning on the mixture proportions. And the way we figured out the best mixture proportion was very experimental. What we did was to do like a grid search of different values between, in this case, 0.75 and 0.89. And the values that were found to be best in the sense of predicting root mean square from DIC are 0.98 for chromium and 0.95 for lead. Now, ideally, we would like the model to have predictive ability, so we would like to predict over locations where we don't have observation. So on top of estimating the mixture proportions, we also fitted spatial Bernoulli model to obtain classification of observation being above, being part of the tail or the body over a continuous domain. So again, we did that because we wanted to be able to predict into locations where we don't have observation. So we need to have a system to generate whether in a given location we have or not an extreme. So the first set of results that I'm showing you here are the results for the body and tail classification. So as a reference, on the top we have the map of the observations that we saw at the very beginning. And on the bottom we have the Bernoulli predictions. So these are basically zeros and one, blues for the zeros and kind of yellow in both ways. So what we see is that the model, the Bernoulli model, captures the pattern of extreme concentrations that we see for chromium, which are the ones here, for example, that are kind of clustered south of the Clyde River, and here in this area in the southeast. In the case of lead, we also are able to capture this pattern of kind of cluster of extremes across the M74. So again, this is not the mixed model. This is only the like an additional step that we needed to do in order to be able to predict everywhere.
We're gonna check what's happening at the bottom right of the chromium.
Bottom right of chromium.
Chromium is on the left side, right?
Yes.
Sorry.
Yeah.
At the bottom right of that figure, as a bunch of orange.
As a bunch of
Orange.
orange here.
Yeah, what's that?
Yeah. So this is the kind of a concentration that we have around them.
So why is it so different in the middle, that's more orange? Oh, this way.
Yeah, so that might be an effect of the way it might be like a different effect together, because here the orange are observations above in the 95% quantum. Okay, so because it was very hard to distinguish the difference at the very extreme level, we decided to have a continuous color scale up to the 95% quantum, and above that is only orange everywhere.
Whereas the Bernoulli predictions.
Wait, what here is just 1 or 0, right? So that might be, I guess, the reason why it looks slightly different. Now, probably it might not be the case as well, but the model is overestimating extremes in this area, but that can be happening as well. Yeah. Yeah, to be honest, I think that what we wanted to get from this set of the model is to have the pattern more or less all right. And I think we got that, but of course, like there might be some issues there in terms of like I was saying, overestimation. Right. So now about the model that I show you. So what we have here are the predicted marginal concentrations. Again, for reference, we have the observations on top, the predictions on the bottom. And these are just marginal concentrations of chromium and lead that were produced within the model jointly, of course. So if we look at chromium, so the left-hand side, we see that the patterns in the overall patterns are well captured. So especially those around the center, those here in the southeast, in the south, the city center as well. The model seems to indicate kind of a raise in chronic concentration around Paisley. So this where the Glasgow airport is located. If we look at the data, we do have some high concentration there, but the model seems to indicate that there is actually a raise of those concentrations compared to the observations. Now, if we look at lead, so what is interesting about lead is that it is a bit tricky to see it here, but we have this kind of a pattern that follows the N74 motorway, and our model is able to capture that as well. We also have some kind of a high concentration, slightly high concentrations in the southeast. And then the port of Greenock over here, as you can see, it is also kind of able to capture that pattern of extreme concentrations. Right. So that's so far what we can tell in terms of marginal concentrations, but as you may remember, oh, sorry, I forgot about this. We, of course, wanted to compare to what will be the standard and the baseline model, and that's like the classical Gaussian fit. And of course, it is what expected. Our model is doing much better. We were expecting to see an increase of the error there because of scarcity of data. That's kind of a usual problem that we have in extremes, because extreme by definition are scarce. But compared to classical approaches, we were doing pretty decently. So, right, going back to what I was going to say is that here I just show you the marginal concentrations, but then of course, what we wanted to have is an idea of how the dependence of the concentrations vary across space. And that's what we are trying to show here in terms of joint exceedances probability map. So we use the UK Environment Agency soil guidance values to compute joint exceedances of both chromium and lead above those guidance values. So the maps that we have here on the left, these are the point-wise estimates of the probabilities. The middle, we have the width of the 95% variable interval, and then on the right, we have the coefficient of variation of the probability. And we did that as a way to come out with a map that can combine both point-wise prediction and a measure of uncertainty. This is easier to communicate. So what we are seeing is that both chromium and lead have high joint probabilities of exceeding the guideline values in the south, in the southeast, and as well kind of at the east of Glasgow around here. And we checked with our colleague at BGS, and that may make sense for him in terms of legacy contamination that is well known. Looking at the uncertainties, they tend to be fairly small, which is of course always good. And then finally, the coefficient of variation, which is defined as the ratio of the standard deviation to mean, shows that areas of high probability, so the ones that we have in the first map here in kind of yellow, exhibit small relative variation. In areas of low probability, so maybe those in the north, so low probability here, if we look at the map of coefficient variation in the north area, they show larger variation in relation to the mean. Right. So yeah, I think that's pretty much it. As a final kind of a points for discussion, probably. I think the most important message is that we show the need to do something else than what is being done at the moment in soil sciences. As I said, the main challenge that we face is the lack of replications of extremes. And what we did, if you kind of dissect what we did, it's nothing like super new. It's just a combination of things. So we took vector models, we took classical models for extremes, and we combined them. And we address the dependence through the sharing components that sometimes are called co-regionalization structures. Of course, we had to kind of take some decisions along the way in order to do something, right? The main one being that we assume that the exceedances are basically stationary. So that's something we needed to do if we wanted to use a proper model for the tail. Now, there are some references there that I mentioned. The paper is under revision at the moment. You can look at the paper, it's on archive. And I'm more than happy to take any question. And I think as the last comment, I want to say it is interesting, I think, how something that is so common in so many different areas, which is to have just the one single replication, hasn't been very well explored. And this was definitely a journey. I know now there are some techniques coming from machine learning. People are combining machine learning with extremes that are able to accommodate lack of replications. At the time when we were doing this project, that wasn't the case. So it was very interesting. Right. So yeah, I appreciate your interaction. I'm happy to take any more questions.
We're a bit close to time, so should we do questions upstairs? And we'll get
Yeah, that's
coffee. Yeah, perfect. Thank you.
Thank you.
Actually, yeah, put down, figure it out. Another thing, hat check problems, we do with your hat problem. It's not really more great, because then it gets too easy to fit there with hat check. The hat check problem is one over here, right responsibility of the arrangement.
Like what?